Every single great invention, from the phone in your pocket to the tallest skyscraper, it all started as just an idea. But think about it. How do you take that perfect, really precise idea from your head and get it into the hands of someone who can actually build it? That's the challenge every engineer faces. And today, we're going to pull back the curtain on the secret language they use to do it.
All right, let's just jump right in. Take a look at this thing. It's got some holes, some weird cutouts, all with very specific dimensions. Now, how would you describe it absolutely perfectly?
And not just to anyone, but to someone who's never laid eyes on it before. You could try, using words. It's kind of like a block with a big hole here and some smaller holes on top. But wait, how big is big? How deep does that hole go? And where exactly are those smaller ones? For an engineer, close enough is it's a disaster waiting to happen. You see the problem, right? Words alone just don't cut it. And that gets us to the heart of the matter. The 3D to 2D problem. I mean, we live and think in a 3D world, but we have to communicate on 2D surfaces, like a piece of paper or a computer screen. So how on earth have we tried to crack this nut? Well, first, there's perspective drawing. This is how artists do it, and it's totally intuitive because it's how our eyes actually see things. You see how the lines of the road look like they're getting closer and are going to meet way off in the distance? It looks real for sure. But for an engineer, this is a huge problem. Those converging lines completely distort the true size and shape of everything. It's totally useless for manufacturing. You can't just take a ruler to this and build something. No way. Okay, so what about pictorial drawings? This is a step in the right direction. It gives us that nice 3D feel, but it gets rid of that weird vanishing point. But look closely. That hole, which should be a perfect circle, it looks like an oval, kind of squished, and angles that should be a perfect 90 degrees look off. Again, for someone who needs to build something with millimeter precision, these distortions are a total deal breaker. And then there's this. This is the solution. It's called a multi-view drawing. Now I know what you're thinking. It looks a little flat, maybe even kind of boring compared to the others. But what you're actually seeing are the individual faces of the object, laid out as perfectly flat, totally measurable views. There is absolutely zero distortion here. This is it. This is how we talk to each other and measure with perfect accuracy. So let's put them side by side. Perspective looks real. Pictorial, easy to picture in your head. But they both have the same fatal flaw, distortion. For an engineer, that's just not going to work. Multi-view is the only one that gives us perfect, undeniable accuracy. The only so-called con is that you have to learn how to see the 3D object from these flat views. But honestly, that's not a con. That's the entire skill you're here to learn. So, what's the secret sauce here? What's the magic that makes this work? It all boils down to one big idea: projection. That's the formal name for the method we use to get a 3D object onto a 2D page. Now, the specific flavor engineers use is called orthographic projection. I know, it sounds super technical, but ignore that long definition. All you need to remember are two words: parallel and perpendicular. That's it. Imagine your lines of sight aren't spreading out from your eyes, but are perfectly parallel, like laser beams, and they hit the page at a perfect 90-degree angle. And this shows you exactly why that's a game changer. These projectors, those lines coming off the object, travel in perfectly straight, parallel lines to the page. Since they never converge, they never get closer together, the image they create is the object's true size and shape. No distortion. That right there is the whole secret to engineering accuracy. Okay, so this orthographic projection thing gives us these perfectly accurate flat views, right? We get a front view, a top view, a side view. Awesome. But that actually creates a new puzzle. How do we arrange them on the page so that any engineer anywhere on the planet can look at it and understand it in the exact same way? Think of it like this. We've just figured out the right words. The front view, the top view, these are our vocabulary. But words without grammar are just gibberish. We need rules. We need a standard layout. Without that grammar, the whole manufacturing world would be like the Tower of Babel, with everyone just guessing and interpreting the drawings differently. It would be chaos. And it turns out the world basically settled on two main dialects for this grammar: first angle and third angle projection. And the difference between them is actually super simple. It's all about the order of three things: the observer, that's you, the object itself, and the plane of projection, which is just the paper or screen. So in first angle, the object sits between you and the projection plane. The easiest way to picture this is to imagine putting the object inside a glass box. You look at it, and you trace its shadow on the wall of the box behind it. But here's the tricky part. When you unfold that box to lay it flat, things get a little weird and counterintuitive. The view you saw from the top actually ends up on the bottom of the drawing, and the view from the left goes on the right side. Now let's flip that for third angle. This one's probably going to feel a lot more natural to you. This time, the projection plane, that glass box, is between you and the object. So you're basically tracing what you see onto a transparent window. And when you unfold this box, everything lines up just like you'd think it would. The top view's on top, the left view's on the back. It's completely intuitive. So which one is the right one? Well, they both are. It just depends on where you are in the world. First angle is the standard all across Europe and in India, but third angle is what's used in the USA, Canada, and Japan. The thing is, in today's global economy, you can't just know one. A great engineer has to be fluent in both languages.
Okay, so we've got the method, orthographic projection, and we've got the grammar, the layout. So let's bring this all home and talk about why this is so much more than just a drawing technique. It's truly a universal language. And this is the part I really want you to take away from all this. Learning orthographic projection is not just some exercise for a class. You are learning a universal language. An engineering drawing is, for all intents and purposes, a legal document. It's a contract that says, build this and build it exactly like this. It is the unbreakable chain that carries an idea perfectly preserved from a designer's mind to a fabricator's hands with absolutely zero room for error. When you master this language, you get the power to create. It's the foundation for literally everything, from a simple little bracket to a rocket ship that goes to Mars. So the only real question left is this. If this is the language of creation, what are you going to use it to say?